In this video, we'll do some more examples of balancing chemical equations using the atom economy method. If you missed the previous video on the atom economy method and the origins for why balanced chemical equations are important, please click on the banner tag above. But for now, we're going to get into balancing chemical equations using this methodology. And so, again, we split the equation down the middle, reactants on one side, products on the other, and we're going to break it down into carbon, hydrogen, and oxygen, the three components here. And again, notice I'm lining up the elements on each side so that I can compare directly. And so one thing to notice about combustion reactions like this is since we have oxygen in multiple places here, we have to be sure that we're remembering to add. And so the amount of oxygen on the product side isn't just the amount in the water, and it isn't just the amount in the carbon dioxide, but it's actually the sum of them. Now, if we apply the characteristics that we looked at last time, again, I've got a pair of subscripts here. If I take those over and turn them into coefficients for the two products, that will help with some of the balancing. Now, small mistake here. I don't actually need 10 of these. I just need 5. 5 times 2 gives me the 10 that I seek. So my carbon goes from 1 to 4. My hydrogen goes from 2 to 10. But my oxygen goes from 3 to, now I have 8 in carbon dioxide and 5 in oxygen. 8 plus 5 is now 13. Now, this provides us with another dilemma. I've got my carbon and my hydrogen balanced as is. Problem is, I don't have a way of getting 13 oxygens on the reactant side, because every single one of my oxygen molecules has oxygen coming out in pairs. So I'm always going to get an even number of oxygens. So how do I get 13 here? Well, the answer is actually really simple. I can do it really one of two ways. I can either cheat the system, and if I cheat the system, I could put in a fraction here, 13 halves or 6.5. And 13 halves times 2 would give me the 13 that I need, and I would have a balanced chemical equation. And if we're dealing in large quantities, moles of each of these substances, that's really not a problem. However, mathematically speaking, it does become a problem if I start thinking about things molecularly. After all, what does half of an oxygen molecule look like? Answer is really don't know. It doesn't really exist in that kind of way. So what you'll see most people do is instead of using a fraction there, starting this over, what they'll do is they'll just double everything. And so what that means is if I start with 2 of the butanes, 2C4H10s, and take it from here the rest of the way, carbon, hydrogen, oxygen, I now have 2 times 4 for 8 carbon, 2 times 10 for 20 hydrogen, and still 2 oxygen at the start. If I carry that over onto the other side, my 4 carbon dioxides now become 8, my 5 waters now become 10, and so once I take care of those, 8 carbons, 20 hydrogens, just like before. 8 times 2 is 16, plus 10 more, 26 oxygens in total. And now 26 is an even number. I can balance and get an even number on the other side with a 13 there. And that's what balances this equation. And so now I have even carbon, even hydrogen, even oxygen. I've got a balanced chemical equation that way. So this methodology and combustion reactions are notoriously the most difficult in this domain. But this kind of methodology is useful. So if we're dealing with molar amounts, if we're getting into stoichiometry, yes, you could use fractions there. However, if we're talking about molecular kinds of quantities, individual atoms, individual molecules, you have to have whole numbers here because there's no such thing as half of a molecule. Let's look at another example. Here's an example of a double displacement reaction. And what's useful to us about a double displacement reaction is we see that we do have some commonality. Sulfate ion is present both in reactant and in product. So when I'm tracking instead of tracking individual sulfurs and individual oxygens, I can track sulfates. And so if I follow this all the way through, one of the other nice things about double replacement reactions is that they're usually pretty easy to balance. You can see already I've got one sulfate on each side, I've got one barium on each side. The only things that are out of balance are the potassiums and the chlorines, which happen to be in the same molecule on the product side. And so they're off by the same amount, which means they can be reset by the same amount. And that amount here is just a 2. 2 KCl's makes 2 Ks and 2 Cl's. And now those are all balanced as well. I've got a balanced chemical equation. So for these last two, I'm going to give you the answers here in about 15 seconds. What I want you to do, pause the video and try to balance these on your own. If you need to break it out and get into the atom economy method, go ahead and do so. If you're feeling confident you can do them just by inspection, that's fine as well. But in 15 seconds, I will reveal the answer. So if you want to do that, go ahead and pause now. Okay, we're back. And here are the answers for the two example problems. Now, both of these were combustion reactions, and combustion reactions are probably the most difficult ones to balance. But if you can master them, if you can kind of get through behind the tricks of them, you can really balance anything. So in the first one, very similar to the combustion problem that we just did, you had to double everything. A little trick that you can look for when hydrocarbons are burning, if you have an even number of carbons, generally speaking, that's usually a sign that you're going to have to double everything. It's not always the case, but if we're talking about alkanes, so simple saturated hydrocarbon burning, butane, octane, decane, those kinds of things, they're going to follow that same pattern. You're going to double the hydrocarbon, and then everything else will kind of shake out from there. This one was probably the more difficult of the two. Um, you have to break out the atom economy there, because what you'll find is that the kind of the key aspect is recognizing that the hydrogen is an even odd split over here. You have 3 hydrogens in the ammonia, you have 2 hydrogens in the water, so you're going to have to go the lowest common multiple route, 6, to get them there. Once you do that, you run into the same problem with the oxygen, so you end up having to double everything. So our next video will concern how we use these balanced chemical equations to actually solve problems and to predict the amount of reactant, the amount of product that we need. It's a process known as stoichiometry. Have a good day.